Yes, class. Good evening. Is this audible to all of you?
Good evening, ma'am.
All are present. Sneha, Sarah, Kulsum, Krishna, Vipa, Hamza, Fatima, and Anand. Fine. See, in the last class we had completed a portion of magnetism and matter. That was your chapter number 5th of NCERT. Now see, some more portions are left from that earth magnetism and all. That we'll do at the end. Now we'll start with your unit 4. Let me tell you first what your unit 4 comprises of. Your unit 4, no, this has EMI and AC. And the weightage of EMI AC together is approximately 8 to 10 marks. EMI and AC both are different chapters. This first one is EMI. This is electromagnetic induction. So that's the chapter 6 of your NCERT. Fine, and then you have alternating current. That's the chapter 7 of your NCERT. So most of the things are combined in this unit. What happens? Things that are present in your EMI lesson. It can happen that they are utilized in your AC. So it's a sequence that is given in NCERT in the correct order. So we will also follow that sequence, which is given in EMI and AC. So first, let us just start with electromagnetic induction. Papers I had shown you, no, class, in the last class. The test papers which you
Yes,
gave.
ma'am.
This is electromagnetic induction. Now see, in this lesson what happens? Maximum things you people are aware of. You have already studied magnetic effects of electric current. You have seen how current carrying wire produces magnetic field. What are the different formulas for it if different shapes are given to you? For its center of the circle magnetic field is different. For the center of the square it will be different. For different shapes it is different. And you also know how to calculate it. Now, in case of electromagnetic induction, no, it is a mixture of your electrostatics and magnetism. So you will see some portion of electrostatics that are getting combined with magnetics element. So in electromagnetic induction word you must have heard of already. Remember when we did our first class, there we had the introduction of this term induction. In induction, we had seen methods of charging, additive properties, and then after all those properties, there we had seen methods of charging: charging by friction, charging by conduction, charging by induction. So one term is there we had already seen this. So now electromagnetic induction, basically, why did this arise? It said that a conductor is there. Before this lesson began, whatever we had studied earlier, I'm discussing that right now. When we had a current carrying conductor with us, so a conductor was there which produced current. So as a result, what did you see? That a current carrying conductor produces what? Can anyone answer this? Current carrying conductor produces
Magnetic.
magnetic. Exactly. So current carrying conductor produces magnetic field. So this was already proven, and this you all have studied also, that yes, obviously current carrying conductor produces magnetic field. That's why you are able to observe all those formulas that you derive, and the formula for if a current carrying wire is going with what will be the direction and magnitude of magnetic field and all. Now the question that was arised by all the scientists was whether if we reverse this, no, if we just reverse this somehow, we have a conductor with us and we take magnetic field. If we have a conductor with us and we take magnetic field, Means if magnetic field exists there and we have kept a conductor over there. Then the question was that will it produce this, the third thing, current or not? This was the main question. So yes, after experiments given by Faraday, Henry, and all these scientists, major contribution was done by this scientist Faraday. All of you heard of this. Capacitance also he has given a big role. So that's why we also use the SI unit of capacitance as Faraday. So Faraday and all these scientists did experiments, did various kinds of experiments, and ultimately they concluded that yes, this occurs. This was proven already. We have already studied this. If a conductor is kept in magnetic field, will there be a presence of current or not? So the answer to this was yes. And you know, this became so important, this whole principle, that it became the principle of AC dynamo. So AC dynamo, we'll see later on, no need to go into the details of it, right? So AC dynamo already gave the principle of it. Now, what was the main law given by Faraday, which we know? But before that, no, we have to have an introduction of a quantity which is known as magnetic flux. Now, understanding magnetic flux is very easy, very easy. All of you have already studied electric flux. Electric flux was what? Remember Gauss theorem? And you know, electric flux, by the way, is more important than magnetic flux because electric flux gets directly linked with your Gauss theorem. Magnetic flux usually comes in combination with Faraday's experiment, so keep in mind. But definitely, separate questions can also. And electric flux that we studied. Does anyone remember what was electric flux that we had studied?
The number of electric field lines that it passes normally to a surface.
Exactly. Yeah. Perfect. See, number of field lines that cross the area normally or perpendicularly. Let's say I have this sheet. These are four magnetic field lines. All of them are making an angle of 90 degrees. So magnetic flux will be what?
Yes, cos theta.
That's the formula. That's the formula. By looking at this, what I have drawn. That you're telling me the formula. I'm not asking you the formula. I'm asking you, this is the figure that I have given to you. These are the number of lines that I have given to you. What should be the magnetic flux? That's the question. See, magnetic flux is what? It's the number of magnetic field lines that will cross area normally. Whatever you studied for electrostatics, electric flux, that's the same for magnetic flux and magnetostatics. So, in electric flux, it was number of field lines. What field lines? Electric field lines. In magnetism, in here, when we do EMI and we are dealing with magnetic flux, it becomes what? Number of magnetic field lines crossing area. So now can anyone tell me what is phi over here? Yes, class. Any idea? Yes, actually. Exactly. This will be 4. See, number of field lines crossing area normally. I have already told you that all these 4 lines are crossing this normally. These are perpendicular to the plane of surface. So obviously, number of field lines means what? You will count it. This is 1, this is 2, this is 3, this is 4. So magnetic flux, this is 4. First, let me write the definition, then I think it will be clear to others. Is what? It is the number of magnetic field lines. See, flux means the same, something that is coming, something that is leaving. So definition of flux is the same. In a case of electric flux, everything gets with respect to electric field. And in case of magnetism, everything gets respect with magnetic field. So number of magnetic field lines crossing and area normal. Or perpendicularly. Or where perpendicularly means the same. You can keep this in bracket. So see the figure that I gave you, this which I had drawn, this means number of magnetic field lines. So how many magnetic field lines were you able to observe? Exact 4 number you were able to observe. That's why magnetic flux will be 4 only, according to this definition. But C class, tell me one thing. If these were what 4 field lines, so even I was able to count it. Now you all will also be able to count it, and who answered correctly, Akifa, she was also able to count it. But what if magnetic field lines are so much that it becomes difficult to count it? It's impossible to count it. If so many magnetic field lines are there. Sometimes magnetic field lines are not given. Magnetic field is just given. This is not the representation of magnetic field lines, by the way. This is the representation of magnetic field. Supposedly, I have say this is a bar magnet kept, and it has the magnetic field B. So obviously, this shows that there are so many magnetic field lines that are making this magnetic field B. But will I be able to ever count it? They are so huge that counting the number is not possible. So one limitation is that if we just directly count it. Second limitation is that what was the second part of definition? Yes, you all have agreed number of magnetic field lines. Second part says crossing an area normally. What if these field lines were not making an angle of theta? Suppose let's say this first one was making an angle of theta with the plane or with anything. Then magnetic flux would be given by these three only. Otherwise, the component of first one. You cannot directly write it like that. So, two limitations are there. First limitation is that number of field lines can be many. You cannot count it. Second is that it can be inclined at any angle. For example, this is the magnet. Now, this is not making an angle of 90 degree with the plane of the page. Suppose this is the plane of the page. So, this is some angle theta. Now, our problem is not solved. How do we calculate the number of field lines if we do not know number of field lines that are passing, or we do not know which field to consider? Then comes the concept of area vector, which we have already studied. Area vector. Can anyone tell what was area vector? Who remembers it?
It's a position vector that is placed normally to the plane of the surface.
Plane of sheet. Yes, any perpendicular dropped into the plane of the sheet. This is your sheet. No, just drop a perpendicular. This becomes your area vector. So B is what? B is magnetic field. N cap is area vector. Area vector means any perpendicular drop to the plane of the sheet. Now, I don't want this theta that is given. This is some random angle with which the plane is making. Some random angle. I need this angle. This is theta. Theta is what? It's the angle between magnetic field and area vector. Area vector is what? Any perpendicular dropped on the plane of sheet. Anywhere. It's not necessary that you draw it at the center. Even at the edges, if you draw, condition is that it should be just perpendicular. Because we need to have certain references, certain points from where we'll call this. Now, theta is what? It's the angle between magnetic field and n cap vector. Fine. Now, how to get the magnetic flux? So, magnetic flux, and let's say one more thing, S is the surface area. S is the surface area. So again, magnetic flux, this is very easy. Yes, last one thing. When you're giving your board exams, in the board exam, this is one thing that you should keep in mind while writing. If it's a question of electrostatics, electric flux, then you can write phi symbol. if it's a question of magnetic flux, or if it's a question of EMI, question from EMI or AC from any other chapter. Class, do mention phi, which one? Phi E? Are you talking about phi E or phi B? Because it may happen that a charge will be kept under the influence of electric field and the influence of magnetic field. So magnetic flux will also exist and electric flux also exists. This is electric flux. This one is magnetic flux. Do mention it. Otherwise, examiner won't consider your answer. Marks can be reduced if a slight strict checking is done. Marks will be reduced. So do mention 5D or 5E. If you see you will be able to analyze. It's a question only from Gauss theorem. You can easily write 5, but it's a question from apart from it. The questions that are extending from the next of the chapters. Then definitely you have to mention whether you're talking about 5B or 5E. So 5B is what? B dot simple. You can write it as BS cos theta. Right? Angle I've already told. This is a scalar quantity you should keep in mind. No need of direction and everything. And SI unit. SI unit is C. Magnetic field is Tesla. Surface area is meter square. So Tesla meter square. Or we also write Weber. You can use any of them. But just remember, theta is what? It's the angle between these two, not the plane of the sheet and magnetic field. Fine. So we have to do certain questions and only this will get clear. Before that, no, just note down all these. Akifa, where were you? You have missed a lot of classes. What happened? Were you not well or something? Everything is fine, Akifa. I think I'm seeing you after 2 weeks or more than 2 weeks. Okay, Akifa, did you take the recordings of what? Have you seen the videos? If not, just let me know. I'll send you then on WhatsApp. And is Sneha here today? Sneha Manoj. Yes, Sneha is there. Sneha, I'll send you all those resolution. I'm compiling it. I've just received and got it for the first chapter. So If you wish, I'll send it only for the first chapter right now. I'll send you the derivations portion. Akifa, just tell me which was the last topic which you attended. See class. One thing that I forgot to mention right now, if the magnetic field is variable, then how will you use it? The magnetic field is variable. Magnetic field is variable. Then your phi b means electric magnetic flux. This will be the integral of V dot. Had the electric field E dot ds is equal to phi, which is equal to q by epsilon. Just forget that Gauss law. Gauss law in magnetism is a very important question that comes not for a huge marker, from your one marker, or it can maximum one markers. This comes Gauss law in magnetism. And do you people have that thing now? Because I think from the COVID time it has been deleted from the website. Do you people have the investigatory project now in your
For
school?
physics?
For every subject, physics, chemistry, biomass.
Teacher, so far
Yes, you.
only for biology it has been announced for us.
Okay, for you it's biology. Okay, for yes, you have it. Yes, investigatory projects I think are there. Even during my time also it was there. Not for all subjects, only for physics. Okay, like Kulsum has only for physics, Atif has only for. So maybe the system is different over there also. It can also happen like that. Or because of COVID time it has been shifted. It's optional. Alright, Kulsum, for you it's optional. So external viva occurs. Like external examiner comes to see your practical portion, or practical is done by the internal teachers. Physics, chemistry, bio, all of them have the practicals. External portion. Alright. Or what about others? This is for Kulsum. External. You have the external examiners, no? Sometimes what happens, sometimes internal teachers are there usually in the class to help you are. All right, for all the subject external exam. See, external examiners ask these kinds of things, which I usually I keep telling in the class, one markers, one markers. Either they do this in your investigatory project, whatever projects you have for the assessment. Either they see it. Sometimes it happens they get very impressed by the project and they do not ask certain questions further. Or it can happen that they can ask questions from your project only, or from anything else. Or it can also happen that in your the external examiner that comes, she may ask questions from the experiment that is given to you. Like experiment in the sense that meter bridge experiment was there. I don't know, I think it's not there right now, but when I was in 12th, meter bridge experiment was there. So the examiner either asked the questions from the meter bridge for the student who got that, or they could ask the random question. A prism is there. Prism is there, I think, now also. In ray optics, you will do prism because it's not deleted. So prism experiment is there to find out the angle of deviation and all. So these things, these external examiners, what they do, this kind of question. If magnetic field is variable, how will you calculate? And especially these kinds of questions. No, the questions I keep on telling you, this can come for a one marker, one marker. All those questions which are short, because obviously derivation they cannot do. Sometimes it happens, they have the sheet with them, sheet and paper is there with them, and they can ask you to write down the derivation, sometimes to prove it also. So that can be different. That happens in colleges, and that is lifelong. But for these questions, you should be ready. Like, what is Gauss law in magnetism? What is Gauss law in electrostatics? So you should be able to differentiate that Gauss law in electrostatics. This is Q by epsilon naught, means a whole definition thing that the charge enclosed is 1 by epsilon, like this. Gauss law in magnetism. So whenever these things come, which you are able to solve it in one line, do remember Viva can come from that. Especially that permittivity question also comes. Remember we did F in air, F in medium, related by epsilon naught and all. This also comes because this is a very, very short question. So this also comes. It can be confusing whether it's F air divided by F medium or F medium divided by F air. What's the right answer? So such kinds of questions are asked by the examiner. Gauss law in magnetism. But if you're able to answer all the questions confidently and from the project or whatever you've prepared, if you're able to answer, then maximum full marks is given. If it's 30 marks is there, so most of the students get 30 or 30. So Gauss law in magnetism is what? What was Gauss law in electrostatics? In electrostatics, it was said that electric flux through a closed surface is what? 1 by epsilon naught times the charge enclosed. This was the electric flux. Electric flux was what? Electric flux through a closed surface, it was 1 by epsilon naught times the charge enclosed. This was given. Now here, in case of magnetic flux, no, this is very important because it gets confusing and it is frequently asked. The closed integral of B dot ds, this should be also equal to something else. This is 0. That's what is Gauss law in magnetism. Basically, this says that magnetic flux through a closed surface is 0. Magnetic flux through a closed surface is 0. So this is important. Few things are there in EM waves where this Gauss law in magnetism is also repeated. And other things are also there. Maxwell's equation and these things will come, that we will see later. But remember, this will be used again. So this only shows because of this, no, that magnetic flux is 0. Why are we getting this? Reason to it? There should be some reason. The reason is that only magnetic monopoles do not exist. Magnetic monopoles do not exist. Right. Magnetic monopoles do not exist, and that we had discussed, yes, in the last class only, I think we had discussed that even if you cut a piece of magnet, the other portion will develop the opposite polarity. For example, if you cut it from north, the remaining portion will develop south polarity automatically itself because monopoles do not exist. Right. And also you can relate it now with the help of example. Let me give you an example. For example, this is north, south, it's a bar magnet. A magnetic field line exists. It is moving. It begins from the north, terminates towards the south, and then from inside it goes from north to south, from south to north. There's a difference between electric field lines and magnetic field lines. In case of electric field lines, they do not form closed loops. If a charge begins, the electric field lines begin from the positive charge, it ends at the negative charge. End. Then they do not meet somewhere. An opposite direction doesn't. In case of magnetics, from here, from north it goes to south. It doesn't stop over there. Inside it moves from south to north. So they form closed loop. Magnetic field lines form closed loop. And let's say from north it is beginning, it is going towards south. So what has happened? This is the direction. Let's say the direction is +1. And the direction is opposite here, -1. So net is what? Net flux is 0. That's why we say magnetic monopoles do not exist. Right, this was one point that I wanted to mention to you all. Now let's start with the question part. So do one thing, just note these 2 points as well, then I'll give you the question to solve. From here, no? From Others also answer, only Atif has answered. Any other answer coming, or should I discuss? Okay, last 2 minutes, then we'll discuss it. Sarah, what's the angle that you considered? Because the only correct answer has been submitted by Krishna. Atif and Sarah, both of you have taken the wrong angle. See, 3 students have only submitted, out of it. Krishna is right. C class. What is it saying? It says that magnetic flux of magnetic flux, magnetic field, flux, magnetic field of 2 Tesla exists in space. Fine, so magnetic field is equal to 2 Tesla. It is inclined at 30 degree with the plane. Magnetic field is making an angle of 30 degree with the plane of the sheet. What do we take when we are writing magnetic flux? We take the angle between area vector and this. This is the angle. Did you understand, class? Why are we taking this angle? This whole complete angle, area vector is what? Area vector is perpendicular. This whole angle is 90 degrees. This much is inclined by it is 30 degrees. How much is left? 60 degrees is left. Why you want to 30 degree? It's with the plane, not with the area vector or with the perpendicular of plane. So magnetic flux is equal to B A cos 60 degree. Area is 10 meters. It's 2 into 10 into half is 10 meters. Any doubts? If you have any doubt, ask me. So, who has submitted? Atif, this is your complete electric flux. You just multiply 2, even if you multiply 2's, then what happened to K cap? Hamza and Akifa, both of you are right. Sarah, negative? How are you getting it as negative? C, class C, tell me. Akif and Hamza, you are right. Others, listen carefully. Magnetic field is given to you. 10 I cap plus 3 J cap plus K cap. This much Tesla is given to you. Area is given to you 2 meters squared. But can you just solve it directly? Can you multiply this 2 with it? Here unit vectors are involved. You also have to write the unit vector. All of you quickly write me in the chat box right now. If the plane is in XYZ plane, then what will be the unit vector for the perpendicular to it? Kept in XY plane, no? Yes, Akif. Others? Hamza, right? Atif, first answer this question what I've asked. If YZ axis are there, means your plane is kept in YZ plane, then perpendicular to YZ plane will lead to you towards which unit vector? Yes, Fatima, correct. Kulsum, right? I cap. Obviously, it will be I cap. See, YZ plane perpendicular to it is what? Towards X axis. So, why did you not people use X axis as the area vector? See, area vector we have to consider. This was given in YZ plane. Suppose this was your sheet. This was the space that was given to you. Perpendicular to it, we'll write it as the area vector. So area will be what? Area will be 2 I cap. Now from here, all of you can easily predict the answer. This is 0, this is 0. So obviously this will be the answer. But let's write it completely. This becomes 10 I cap plus 3 J cap plus K cap dot 2 I cap. If you wish, you can write it as 0 J cap plus 0 K cap like this. Now see this, all these multiplied by 0. This gives you 10 into 2, that is 20. I cap dot I cap gives you 1, so only 20 vectors. This is the answer. Just note it down quickly. Any doubts till now? Now see, certain experiments were done by Faraday. Faraday and Henry, both of them conducted the experiments, Faraday's experiment. They call it as Faraday's experiments in EMI. So electromagnetic induction and everything, the definition and everything comes from here. What is electromagnetic induction in detail? I'll tell you right now, but first understand the experiment of Faraday. Why do we call it, why do we have the heading of this lesson as well? See, Faraday's experiment was what? He did certain experiments to which he concluded certain things. What he did was, in his experiment, he took a copper insulating wire and wound it in the form of a circle, like this, random circle. If you make it by your hand, and one of its end, it connected to a galvanometer, and he connected its other end to the other side of that, like this. Fine. This was a circuit. And not only this, one more thing, how will the current flow without the battery? So definitely battery was also connected. Now what happened? A bar magnet was brought. This is the first case. A bar magnet was brought. Let's say this is North Pole, this is South Pole of the bar magnet. The bar magnet was brought closer to it. The bar magnet was brought, let's say V is the velocity of the bar magnet, and it was brought closer to the loop of it. Now, current was obviously flowing. Current started flowing, and what was observed? That galvanometer showed a slight deflection. A slight deflection was shown by the galvanometer. Fine, this was one thing. Then what did he do? Secondly, he took the same apparatus. This was the loop. Loop was rough loop, not a proper circle. Just by that you can create by yourself. Galvanometer and the battery. Now, this time, North Pole, South Pole, this time the magnet moves away from it. Here the magnet is moving away from it. Then he observed that current also flowed. Again, current flowed, but this time in opposite direction. So galvanometer again showed a deflection, but in opposite direction. Slight deflection was observed. Third case. Third case, what he did, see, nobody is going to ask you to write all these experiments in detail, but again, for your knowledge, you have to have these because the upcoming portion and the topics and the formulas are based on this. Now, lastly, what did he do? This was the closed loop. And other experiments were also performed by Faraday and Henry. So don't get confused by that. We'll just see this one. Now, what did he do? He kept the magnet static. Magnet didn't. What was observed? There was not a single deflection by a galvanometer. What were the experiments? See, I'm repeating. When bar magnet was brought closer, galvanometer showed deflection. When the bar magnet was brought away, this also showed deflection. Difference is that in opposite direction. And when the bar magnet was kept stationary along with it, means no magnet was moved. So what happened? No deflection. No deflection was observed. So what can we conclude from these experiments? Certain things we can conclude. Certain regions are also there associated with it. See, what are the possible reasons that happen? Understand this carefully because the upcoming portion of Faraday's law of EMI, that is a very basic portion and very easy portion. See, again, I'm telling you, this is an easy lesson. You won't be facing difficulties in this lesson if you understand and get it revised on a regular basis. It's a short lesson. EMI is a short lesson. AC, both of them are short lessons. EMI is very much easy. Many students find AC alternating current difficult because trigonometric functions get involved and most of the things are there. But EMI is a very easy formula based chapter. Just understand Lenz's law, understand few formula, you are done with the lesson. Because maximum things you have already studied in magnetics. So conclusion was that whenever this bar magnet came closer, because of these magnetic fields, what happened? As it was brought closer, the field line, number of field lines got increased. number of field lines that it got increased. But as soon as this bar magnet was moving away, the number of field lines they got decreased. And in the third case, what happened? There wasn't any magnetic field line produced because no deflection was given. So what is the conclusion from the first one? As the bar magnet came closer, magnetic flux linked with the coil, this increased, and EMF is going to induce in it. EMF is going to induce in it. Obviously, EMF is there in this circuit. That we call it as induced EMF. That induced EMF increases, and so the current increases. That's why this deflection we were able to observe. What happened secondly in this experiment? Magnetic flux linked with the coil decreased. So the induced EMF decreased, and so the current decreased. That's why you were able to see. Here there wasn't any change in magnetic flux. There wasn't any change in magnetic flux. So EMF, induced EMF was also zero, induced current was also zero, hence no deflection was observed. Now two important points I'm going to make you people write, which you have to remember. Or just let's start with the formula. From here, that is included in that. Very important point is the two important points in Faraday's laws of EMI. This is actually a single law. 2 points means two important conclusions from the single point. Law is same. So Faraday's law of EMI says what? Whenever, see, listen this carefully. This is important and this is very basic for your induction, self-induction, mutual induction. Whenever magnetic flux means your phi, magnetic flux, linked with a coil changes. Alright, this changes. What happened? EMF is induced in this. EMF, you all know, electromotive force, whose SI unit is volt and everything. That same EMF, whatever you have studied, no, for EMF. That's why we have done it already earlier in current electricity. That same EMF. That changes. There's a change in that EMF. And that induced EMF, no, this is what? Changes, and EMF is induced in it. And this is the first point which you have. See, law is the single law. Yes, single statement is there. In two parts, you should be able to understand. So whenever this changes, this occurs. And what happens further? Further is induced EMF is proportional to rate of change of flux. If this can come in your bar marker and as discussed that by one thing that happens. So rate of change of flux is what? dt over d phi over dt. Let me write it here. See, let's say phi. Let's do it in detail. Phi 1 is what? Phi 1 is flux at, let's say, time instant t1. Phi 2 is flux at time instant t2. So delta phi will be what, Fatima? Delta phi. Change in the flux.
Flux at time instant t2.
Change in flux. Change. How do you calculate the change?
Initial flux
Minus final flux. Exactly. So initial final flux, that is phi 2 minus phi. Perfect. Fine. This is time instant t1. That is time instant t2. Also, can you tell what is the time difference? Time interval. Yes, Kulsum. Time duration, time instant. What should I write? Change in time. Sneha? Time instant is given to you. Time interval I'm asking. No idea, Sneha? Yes, right, Sarah. See why you people are not able to understand this. Final time minus initial time. That is what? T2 minus T1. Clear now, Sneha and Kulsum? T2 minus T1. So, according to Faraday's law of EMI, he says that induced EMF, this is directly proportional to rate of change of flux. What did I tell you earlier? When anything gets divided by distance, we call it as gradient. Remember potential gradient we had. And when anything gets divided by time, we call it as rate. This is known as gradient. Anything changes by position, anything changes by time is rate. So it's directly proportional to rate of change of magnetic flux. Let's say a constant is there. Now, in the system that we follow, SI system that we follow, K is given as 1. Therefore, electric flux is minus delta phi over delta T. Now, why do we add this minus sign? That we'll do in length. That we'll do in detail in length, because this is there in your syllabus how to solve it. Fine. So this is what this. Remember, we had done average current and instantaneous current. So this will be average EMF. If you have to find out instantaneous EMF at a particular time, instant if it is asked, simply minus d phi over dt. Similar pattern that we have been doing. Remember, for current also we did. Delta Q divided by delta T was the average, and I is equal to dq over dt was the instantaneous. Similar here. So this gives you instantaneous EMF. Now, if induced current is asked, then what will you do? For induced current, see, if R is the resistance, see, resistance will be given to you, or there will be a way to calculate the resistance. So, current will be what? Current is EMF divided by resistance. That becomes minus 1 by R delta phi or d phi over dt. So, current is what? Induced EMF. This is minus d phi R like this. One last thing, what if charge is asked? Just in case no charge is asked. So you can write current as what? Current can be written as charge multiplied by time. Charge is charge divided by time. This is Q is equal to IT. Current is charge divided by time. That becomes dq divided by dt is equal to minus d phi R over dt. dt gets cancelled. dq is what? Minus d phi over. If charge is given to you, where your q is the charge, this is your magnetic flux, this is your resistance. So let's do certain questions of this. We start with the very easy questions, but first note it down. This Faraday's experiment from here, and wherever you people have doubt, ask me first. See, for this flux is given to you, this is a variable flux. So we have done these kinds of question for current. So for the A part, flux at 2 seconds calculate. Just put 2 everywhere instead of T plus 1. So this is the final flux that we have calculated, that is 17 Weber. What's the initial flux? Means T is equal to 0. Just put 0 everywhere instead of T. That becomes 1 Weber. Now, final time T2 is given to you as 2 seconds. Initial time is given to you as 0 seconds. So delta phi over delta T you have to find out, because that's the induced EMF's value. So here induced EMF will be 17 minus 1 divided by 2 minus 0. That becomes 16 divided by 2, which is 8 volts. For the calculation of the second part, B part, EMF is what? D phi over dt. Again, I'm telling you that direction thing we will do it in Lenz law. Lenz law is just based for your direction only, how it opposes the cause that it produces it. That we'll see later on. Right now, let's differentiate it. So phi is given what? 3t square plus 2t plus 1. No. So if you differentiate this, 3t square becomes 60. 2t becomes 2, 1 is 0, that is 6t plus 2. Now at t is equal to 2 seconds, you have EMF as 6 into 2 plus 2. So this is what? This is 14 volts. This is the answer. Anybody who is facing difficulty in differentiation or integration, first differentiation, anyone who wants to clear the basics, very basics of differentiation, not those for the students who already know. If you wish, you can attend the class on Sunday, 11 p.m. timings, KSA timings.
Teacher, you need to take negative.
Yes, Atif?
Teacher, do we not need to take the negative? Like it's minus
Negative
dq by
sign,
dt, right?
see, it's minus q by dt. That's what I was saying. It's minus dq over dt. This is the magnitude. Fine, this is the magnitude that happened. If you write the minus 8, you can write it as minus 14 volts and minus 8 volts as well. I was saying this negative sign. Now, why do we consider this negative sign? This negative sign has a full significance that we'll see. So, according to you, if you are right now, I was just asking you to calculate the magnitude. So that's why I ignored that negative sign. But for a full-fledged question, once we'll do Lenz, automatically you will be in a habit of writing that negative sign. Fine. So, yes, I was saying on Sunday, if you need a class on differentiation, just let me know. I'll send you the meeting ID then. 11 a.m. KSA timing, 1 hour class. Very basics of differentiation. For those students who are able to differentiate the basic thing, no need to attend that class. Then you'll get bored by it. For all those who want just a very basic class, how to do it, which we did in potential and capacitance, just let me know. I'll send you the meeting. All right, fine. Just note it down. And as you complete it, just write done in the chat box. All right, class, and you can leave, then we'll continue in the next class. Just be prepared with the derivations, and Sneha, by today or tomorrow, I'll keep on sending you. All right, Fatima, I'll send you the link, and anyone wants to join the class, let me know. Otherwise, that's a very basic class. For all those who are able to do that basic differentiation, you will get it.